classes, Ms. Wiles, in this video, we'll probably be doing 14 through 18 or something like that as we go through some other examples for the North Carolina final exam for pre-calculus. Now, looking at number 14, you should have already looked at it. You're looking at it now. And so you're thinking about, okay, what can I do? And most every high school student, if they're not familiar with substitution as a strategy to use on multiple choice exams, they are really failing at this game because substitution works so well so many times. So you go through, and I don't have all of this to show you, but you go through and substitute -1 if you're checking A for the left-hand side of the equation and the right-hand side of the equation. If the left-hand side of the equation equals the same thing as the right-hand side of the equation does, whenever you make that substitution, you would choose it. For -1, it doesn't. -2, however, does work. But then you look at your other answer choices. You can already get rid of D because it had the -1 there, and 2 doesn't work anyway. But C has a -2 and a 1, so we have to consider the 1. Now, we can just use straight substitution and do it, but we should be observant and see that 1 minus 1 in a denominator gives us 0, and the denominator cannot be 0, and therefore C cannot be an answer either, and we'll default to B because it works. Yep.
That's a shame.
Yeah. Number 15, what is the range of the inverse of y equals tangent x? Well, if you know how to use your handy-dandy calculator, then you should be able to do this, as long as you know, number 1, what is the inverse of tangent? Number 2, how do we graph it? So, the inverse of tangent is not cotangent, it's arctangent. So, I can graph y equals arctangent of x. That's the inverse of the tangent function. So if I graph y equals the arctangent of x, if I make that graph, first of all, I'm going to want to make sure that I put that in y equals, and that instead of just hitting graph, because it's not going to look very pretty if I do, I'm going to hit zoom and zoom trig, zoom and z trig. When I hit zoom and z trig, my graph is going to look like that. Now, when my graph looks like that, and yours might not be in color, but it's still going to look like that. When my graph looks like that, I should be able to automatically, with no question, eliminate C and D, because Y are these values that we see here. How high does it go? How low does it go? And then I have to, they've been very kind here, I just have to determine, does it include the -pi/2? Or does it not include the -pi/2 and the pi/2? And if you remember, these kinds of values, these kinds of graphs, these kinds of functions, these kinds of trigonometric equations, they're never going to actually hit that value. They're just going to be very, very close. So close that you wouldn't be able to tell the difference. The answer is A. Now, one thing that you do want to remember is when you're looking at these kinds of graphs is what are these values? And so whenever we do hit zoom trig, this is pi/2, this is pi, this is 3pi/2, or pi and a half, or 1.5 pi, and then 2 pi. And of course, then we have our degree measures also of 90, 180, 270, and 360. You should be very, very familiar with angle measurements by this time. So that's all I have to say about that one. Hold on, I got to go back into this. Oh, I've messed it all up. Don't even know where I am. I'm going to bring this back down, try to get things. Okay, we're going to pause. All right, I think I've got it fixed. Let's go here, let's go there. It was pointed out to me, and it's true, I did label these wrong. I always do something wrong. The first one would be pi/4, pi/2, and you can see how close that gets to pi/2, but as it continues, it's never going to quite hit it. So I'm sorry, and let's go on to another problem. Number 16. This is a classic pre-calculus question because it's going to use the law of sines. And you may not have looked at it yet, but if you haven't, pause it and go ahead and look at it. We're going to need some kind of drawing to go along with this. James is standing 10 meters away from Samantha. So I'd start with that sentence and I'd draw it. Here's James. Maybe I should put it down a little bit further. Here's James. Here's Samantha. They're 10 meters apart. A bird is located in the sky at a point between where James and Samantha are standing. Here's the bird. It's somewhere between them. James is looking up at the bird. Apparently he's laying on the ground. I've always thought that with these kinds of problems, that he must be laying actually on the ground with his eye on the ground, and he is looking up at the bird. Okay? But the angle of elevation, and they are basically, because either way, otherwise they have to be exactly the same height, but we're not even going to go there. So this angle is 74 degrees. It's pretty close. It doesn't even matter because it's a sketch. Samantha is looking up at the bird at an angle of elevation of 47. Now that doesn't look like 47 degrees, but we don't even care. We're going to let the numbers do the talking, not what it looks like, okay? So we need to find out approximately how far is the bird from Samantha. That's this one. We'll call it little j, just because it's opposite the j angle. That's what we want to find. When we know two angles and the side in between, and we're looking for another side, we should be using the law of sines. You only use the law of cosines when you only know one angle and you know two sides. So law of sines comes along and I'm like, okay, that's what I'm going to use. So because I want to use that, I'm going to lose the whole story. And I know that the ratio is that the sine of, I thought that bell would never stop. The sine of James's angle, the 74 degrees, over the little j is equal to the sine of 47 degrees over, and then I'm like, no, that doesn't work. Because I don't know this one. So I think, okay, what else can I do? What else can I do if that doesn't work? And it's not a right triangle, so I can't do anything like that. But I should easily be able to tell what this angle is. What is that angle? And I should be able to do that because when you have three angles, you've got a triangle. When you add all three angles together, you should have 180 degrees.
59 degrees.
And that is 59 degrees. So that's the angle that I will use to correspond to 10. And I'll use sine of 59 degrees over 10. Now, I'm the type of person, I don't like to get my calculator out until I've got everything set up. So I'm just going to make it so I can just put one thing in the calculator at all. And so when I look at this, it's a proportion, and we did these way back in middle school. So we cross multiply and divide.
Yes, sir.
So I have 10 sine of 74 degrees, and I've just cross multiplied, divided by the sine of 59 degrees. It's not until I know that that is what I'm going to put in my calculator that I take my handy dandy calculator, and that's what I do. And that's when I get the answer. You can definitely expect to see the law of sines and the law of cosines. I'd be certainly surprised if you didn't. And you should be able to do inverse functions. And here we have an inverse function. Now, if you remember, if you are working on this at home, you're pretending that I don't have the answer there, and we're going to go on. But we're going to change this around so that you can do it. So we have y equals the log base 5 of 2x minus 1. That's what y equals. That's just what they say. And so to be able to do the inverse function, I need to switch the x and y. So now x equals the log base 5 of 2x minus 1. At this point, we need to understand And thank you to my class that you didn't hear. We're switching the x and y, so this would be 2y minus 1. Now, understanding how logs work, and we're not talking about some log out in the middle of the woods that you don't want to turn over because all the nasty bugs are under it. We're talking about logarithms. We're talking about a logarithm that is an inverse function of exponents. The way that it works, this is called your base. This is your base. So what this is saying is that 5 to the x power is equal to 2y minus 1. That's just how it works. This value, when you have a logarithmic function, this value that I just circled is your base. This value that I'm putting a square around, that's your exponent. And then this value is your big number. It's just your big number that's going to be all by itself. So now we need to solve this for y. Solving this for y is a very simple two-step process that we need to do here. And the first one is to add 1 to both sides. So we add 1 to both sides. We have 5 to the x plus 1 equals 2y. We divide both sides by 2. And we have 5x plus 1 over 2. And that is our answer, B. And next, what is the value of the limit shown below? Now, could you put this in the calculator? Yes, you could. In fact, I didn't think about it, so let's pause and do that. There are two ways of thinking about this problem. At least there are a lot of ways to think about it, but there are two ways to think about it to get to the right answer. The first way is to use your handy-dandy calculator. So I graphed it, went into y equals, and just used x for n, 3x minus 1 over 3x. When I graph it, I'm looking at it and I'm thinking, well, as x approaches infinity, I have to think about the x values getting larger and larger and larger. If what I see happening here continues, then it looks like this value is somewhere, if I look at the y-axis, the value of that function is never going to get above this level. Now, 2/3, so that tells me that it's not going to be positive infinity. If it were positive infinity, as x got larger, I might not be able to see it on this screen, but I would definitely see the values of y just getting larger and larger. This is obviously not getting larger and larger, and I can look in my table and I can see that it's not getting larger and larger. Well, it is, but it's not getting like larger than 1. Look at the numerator and the denominator and how close it is together. Just going down to x equals 8, it's 6,560 over 6,561. One more value, one more number in the numerator would give me a value of 1. So obviously this is more than 2/3, but less than 1. And if I continue, if I just wanted to calculate the value when x is 1200, it's probably not going to let me because I don't think it's part of my screen here. But I could do that like on the main screen or something, and I would still see a fraction that was just, it's close to 1, but not 1. At the same time, I'm going to keep on going. We're looking at the table. We'll go back to the table. I've got to quit and tell it, okay, I know I made a mistake. So we go back into the table and we continue looking. Well, I've got some decimals here. I keep on going and it's a 1. Now you may think that it actually reaches 1, but it doesn't. It gets very, very close. The calculator rounds it off. The calculator stops at a particular point and says, okay, fine, you're close enough to 1. I'm just going to say that it's 1. And that's really what it does. But the other way of looking at this is thinking about x as x gets larger and larger and larger. As x approaches infinity, the denominator is going to approach an extremely large number. Would you agree with that?
Correct.
The numerator is also going to approach an extremely large number that is just one less than the denominator. So even just thinking about what's happening as x is approaching this extremely large number of infinity would tell you that eventually they're so close together that it might as well be called 1. And that's what you see happening in your calculator. The good thing is that on this particular problem, you see it happening very quickly. That's all I have to say about that, and you can go to the next video if you'd like to see the next set of problems.